Hello viewers, welcome to video number 89 of the channel MALACHEMPHILIC. And video number 89 is the 30th episode of Chemical Thermodynamics. And the topic is Carnot cycle, practical implications. So let's start. In my last video, we have discussed Carnot cycle and we have derived the formula or equation for the efficiency of the heat engine. And efficiency eta has come out to be eta is equal to T2 minus T1 divided by T2, where T2 is the temperature of the high temperature reservoir from which the heat engine is absorbing heat, and it is converting a part of the absorbed heat to mechanical work, and remaining part it is releasing to the low temperature heat reservoir or sink, whose temperature is T1. So T1 is the temperature of low temperature sink, T2 is the temperature of the high temperature heat reservoir, that is source. Okay. So this is the expression of efficiency or eta, which is denoted by eta. This we have observed in my last video. So this I can write it as 1 minus T1 by T2. T1 by T2. Now look at here. The efficiency of the Carnot heat engine depends on the temperature difference of the source and sink, or in other words, it depends on the temperature of the source and temperature of the sink, but it is independent of the nature of the working substance. In Carnot heat engine, the working substance is ideal gas. So whether you take hydrogen gas, oxygen gas, or whatever it is independent of the nature of the working substance or the ideal gas. It depends only on the temperature of the source, that is high temperature heat reservoir, and temperature of the sink, that is low temperature heat reservoir. Now from this equation, one thing we can know that this eta cannot be 100%. Okay. Why eta cannot be 100%? If the efficiency is 100%, how that is possible? So, if efficiency is equal to 1, that is 100%, then either this T1 is equal to 0, or from this equation you see, or T2 should be is equal to infinity. If T1 is 0, then this part will be 0, then efficiency will be 1, that is 100%. Or if it's T2, which is in the denominator, if that is infinity, then this part will be 0, then also efficiency 1 or 100%. But that is not possible. T1 also cannot make it 0 and T2 also cannot be infinity. So efficiency can never be 100%. This is one conclusion. Now, second conclusion from this equation, what we can draw? Look at here. Efficiency depends on the temperature difference here. Now, for a particular temperature of the source, if the sink temperature decreases, that means if T1 decreases, then efficiency increases. So, for a fixed temperature T2, if sink temperature, if T1 decreases, that is sink temperature decreases, eta increases, that is efficiency increases. And what is the other one? For a particular temperature of sink, that is T1, if T2 increases, then also this difference will increase. Then when this difference, look at here, if T2 increases, okay, then what will happen? This part will be still and still more smaller, so efficiency will increase. For a particular temperature of T1, if T2 increases, that means this part decreases, so efficiency will increase. So what we can write? For a fixed temperature T1, so this one is fixed. If I increase the T2, if T2 increases, then efficiency eta increases. Okay. Now, coming to the next point, that is the practical implications. See, in Carnot cycle, we have observed that all the 4 steps are reversible. And you know, in the reversible process, work done is maximum. But reversible process cannot be carried out practically. So, using Carnot cycle principle, theoretically what efficiency value you can calculate, practically that much of efficiency of a particular heat engine cannot be obtained, because practically you cannot carry out the reversible process. The process will be irreversible, where work done will be less. That means net work output will be less. So, Carnot cycle will give some theoretical efficiency value. Practically, you cannot reach up to that value because reversible process cannot be carried out. But still, Carnot cycle important. See, though no heat engine can achieve Carnot efficiency, Carnot cycle serves as theoretical benchmark. Researchers and engineers strive to get as close as possible. See, using Carnot cycle, that means using the equation of efficiency, eta is equal to T2 minus T1 by T2, whatever efficiency will be calculating, then that will be the maximum. Then researchers and engineers, they will always try to get the efficiency of the machine close to that. They cannot reach up to that value, but they, by improving the design, by improving the construction or any parts, they will always try to achieve close to that value. So this Carnot cycle efficiency value is a benchmark. That will be benchmark. We have to reach as close as possible. So that is a benchmark to the engineers and researchers. They will try to improve the design, they try to improve the construction so that they can get the efficiency as close as possible to the theoretical value calculated by using Carnot cycle principle. For example, high efficiency gas turbines and some advanced power plant incorporate principles inspired by Carnot cycle. Okay, this advanced power plant, high efficiency gas turbines, they have taken that principle of Carnot cycle and they have construct that device to get the high efficiency. Now, the second practical implication, the application in refrigeration. Carnot refrigeration I will explain in my next video. Now coming to the third point. See, you know that entropy is another thermodynamic quantity which signifies the randomness or disorderness of the system. Okay? And already I told you in my previous videos, heat cannot be completely converted to mechanical work by any heat engine. A part is converted to work, remaining part actually goes to increase the entropy. Okay, and when I'll explain entropy in my coming videos, you will observe that this concept of entropy has been derived from Carnot cycle. Okay, and already in Carnot cycle you have seen that energy transfer, that is transformation of heat energy to mechanical work, how it is related to the temperature, that is temperature difference of the source and sink. So all over the Carnot cycle is giving the connection between entropy, temperature and heat transfer. Okay. Now the last point, the Carnot cycle principle gives researchers in developing eco-friendly technologies, emphasizing the importance of minimizing waste heat and optimizing energy use. To increase the efficiency of the heat engine, what you have to do? You have to minimize the waste heat. That means minimize the amount of heat which is going to the sink, because we know that eta is equal to, that is T2 minus T1 by T2, or in other words you can write that is equal to Q2 minus Q1, Q2 minus Q1, that is eta, divided by Q2, and that we can write W net by Q2. All these things we know. Okay. So this Carnot cycle principle, it helps us in developing eco-friendly technologies. Why? It gives emphasizing on the importance of minimizing the waste heat. That means if the heat which is going to the sink, that is the waste heat, if that is less, then eta value will be more. So it is giving the importance of minimizing the waste heat and optimizing the energy use. That means more energy converted to work and less amount of heat is going to as a waste heat. So these are the practical implications of Carnot cycle. In my next video, we will discuss about the refrigeration, Carnot refrigerators and Carnot theorem. Thank you.